After studying this module, you shall be able to define a symmetry product involving number of symmetry operations, perform symmetry operation on a point in Cartesian coordinate system, learn number of examples of performing symmetry operation in succession, some general points about relation between symmetry operation and symmetry elements. We have earlier seen that total number of symmetry elements present in a molecule and total number of symmetry operations generated by them. It is also learned that symmetry operation constitute a group. In this module, you will see the net result or product of 2 or 3 symmetry operations which have been carried out successively in a particular manner. Such types of product of symmetry operations are very helpful in dealing with the applications of the group theory in chemistry. What is a product of symmetry operations? In a group X, Y, Z and E, let us take the symmetry operation X and Y and combine them in the manner Y X is equal to Z. X and Y symmetry operations have been carried out in a particular manner and the net result is Z, which is also the element of the group. There is a definite rule or notation that must be followed when we carry out the symmetry operation. First, we carry out the symmetry operation which is written in the product like this, that is right to left. If I write down the product Yx is equal to Z, then what I have to do? I have to perform the operation X first, then operation Y. That is, right to left rule is to be always followed while taking this direction of arrow indicates the order of performance of the symmetry operation. X performed first followed by Y. If we do not follow the order from right to left, we may get different result. If the product XY and the product Yx are the same as Z, then we say that X and Y commute with each other. And if the product XY and Yx are not same, then XY and Yx do not compute with each other. That is, the products are not same, then X and Y do not commute with each other. In abelian group, all group elements commute with each other. If we apply first symmetry operation X to a point X1, Y1, Z1, it will go to a new point X2, Y2, Z2, and on further applying a second symmetry operation Y, let X2, Y2, Z2 goes to the point X3, Y3, Z3. That is, the net result of carrying out 2 successive operations is a point X3, Y3, Z3. Now, let us look a way, that is another symmetry operation or the third symmetry operation Z, which will carry out the point X1, Y1, Z1 directly to X3, Y3, Z3. If it is there, then we represent the procedure as shown. So, Z is the product of the operation Y, X, Y carried out on certain points. Let us take few examples to explain the meaning of symmetry products. If there are 2 C2 axes perpendicular to each other in a plane, then there must be another C2 axis perpendicular to the plane of both the axes. That is, if there is a C2x and C2y axis in the molecule, then there will be a C2z axis into the molecule, or we can say C2y into C2x is equal to C2z. This we can prove by taking a point in Cartesian coordinate system. Let us take this Cartesian system and a point as shown in. Now, what we see over here, we operate C2x clockwise first right to left rule. On general point x1, y1, z1 of an arrow up in first quadrant, it goes to point x1 minus y1 minus z1 and arrow down in second quadrant. On further applying C2y clockwise, it goes to point minus x1, y1, z1 in third quadrant, arrow up. Now apply C2z clockwise to the original point, arrow up, x1, y1, z1 in first quadrant. It will take this point to a point minus x1 minus y1 z1 into the third quadrant. It is the same result as has been obtained by carrying out C2x and C2y successfully on general point in first quadrant. Thus, what we see, C2y into C2x is equal to C2z. Let us take second example. Show that if a molecule has C4z and C2y axis, then there must be a C2 axis lying in first and third quadrant of xy plane at 45 degree to C2y. That is, prove that C4z into C2y is equal to C2 lying in x and y plane in first and third quadrant. Again, to show this, we have to take the help of Cartesian coordinate system and carry out the symmetry operation. Carry out symmetry operation as follows: C4z, C2y on point x1, y1, z1. First perform C2y on x1, y1, z1 in first quadrant. It will take the point to its new position minus x1, y1 and minus z1, arrow down in fourth quadrant. On this new point, now perform C4z. New point obtained is x1, y1 minus z1 in first quadrant. We get the same result by perform C2 operation on x1, y1, z1 about the axis lying in first and third quadrant. The results are show that C2x and sigma xy commute with each other. That is, you have to prove C2x into sigma xy is equal to sigma xy into C2x. Again, we will use the, now here you can carry out the symmetry operations and you can prove yourself that if you carry out the C2x and sigma xy in either way, the net result will be that sigma 2x into sigma xy is equal to sigma xy into sigma 2z. You can take the Cartesian coordinate system and it will be as shown. You carry out these two, you will get the same result. It means C2x and sigma xy, they commute with each other in this manner.
In example 3, we need to show that C2z and sigma xy commute with each other. That is, show that C2z dot product sigma xy equal to sigma xy dot product C2z. The figure shows the product of symmetry operations. First, C2z dot sigma xy. Second, sigma xy dot C2z. Thus we can see that the final results of first and second roots of taking the products of symmetry operations are get the same result. Thus C2z dot sigma xy equal to sigma xy dot C2z. That is, C2z and sigma xy commute with each other.
Let us see now the symmetry products of some symmetry operation in a molecule trans-dichloroethylene, which belongs to a particular point group we have not discussed so far, that is D2H. Trans-dichloroethylene has four symmetry operation in it: E, C2, sigma xz and I, which are shown. These four symmetry elements generate only four symmetry operations E, C2Z, sigma x, y and I, and this constitute a group of order 4. Now, let us take the symmetry products C2Z and I and symmetry product I and C2Z. These symmetry products in this molecule, on applying C2Z and I, the configuration 1 goes to configuration 2nd, then it goes to 3rd. On applying I and C2Z, the configuration goes from 1 to 4 and then to 3. Therefore, C2Z into I is equal to I into C2Z, and these, that is I and C2Z, they commute with each other. Now let us take this trans-dichloroethylene molecule and try to prove our point, that is the operation I followed by C2Z is equivalent to operation followed by C2Z into I. Now first let us take I operation on this molecule. Here the center of inversion lies into space. So this chlorine and this chlorine are interchanged. This hydrogen and these hydrogens are interchanged. Now if I carry out C2Z operation, then I will get a configuration as shown in this over here. If I carry out C2Z operation first, then carry out the operation I will get the same result. That is C2Z, C2 operation carried out along Z axis and I operation combined in either way. That is either I then C2Z or C2Z then followed by I. You will get the same result. It means these two symmetry operations in this trans-dichloroethylene commute with each other, and net result is the same, C2Z followed by I or I followed by C2Z, you get the same result. Some general points about relation between symmetry operation and symmetry elements can be cited like this. Rotation can be created by combining reflections, but reflection cannot be created by proper rotation. Cn axis and one perpendicular C2 axis requires the existence of n C2 axis perpendicular to Cn axis. Product of two proper rotation must be a proper rotation. If there is a Cn axis and a plane containing it, then there must be n such planes separated by n is equal to 2 pi divided by 2 n angles. The product of two C2 rotation about axis which intersect at an angle of theta is a rotation by 2 theta about an axis perpendicular to C2 axis.
Now we will see the developments in symmetry in chronological order. In around 400 BC, Plato classified the 5 Platonic solids. Platonic solid are any of the 5 geometric solids whose faces are all identical, regular polygons meeting at the same 3-dimensional angles. These 5 special polyhedra are the tetrahedron, the cube, the octahedron, the icosahedron, and the dodecahedron. Moving further, in around 300 BC, the geometry of polyhedra was described by Euclid. Then, in around 1528, De Symmetria Partium, which is a study of symmetry in art, was given by Albrecht Dürer. Then, in 1611, de Neve Zexengula Kepler studied the hexagonal symmetry of snow crystals. In 1830, J.F.C. Hessel derived the 32 crystal classes starting from the law of rational indices. In 1849, Auguste Bravis derived the 14-space lattices in 3 dimensions. In 1860, Louis Pasteur discovered the connection between optical activity and an enantiomorphic. In 1872, Felix Klein proposed the Erlangen program, where geometry is classified by invariance groups. In 1878, Arthur Cayley formulated the abstract group concept. During 1890 to 1891, A. M. Schoenflies and E. S. Fedorov derived two 30-space groups in 3 dimensions. They both derived these independently. In 1918, M. E. Noether showed the general connection between symmetries and conserved quantities. Hans Albrecht Bethe was a German and American nuclear physicist who, in addition to making important contributions to astrophysics, quantum electrodynamics, and solid-state physics, won the 1967 Nobel Prize in Physics for his work on the theory of stellar nucleosynthesis. In around 1929, Hans Bethe derived the splitting of atomic levels resulting from the crystal field symmetry, that is, crystal field theory. In 1930, Eugene Wigner studied the effects of the symmetry of molecular configurations on the vibrational spectrum. In 1931, Linus Carl Pauling, an American chemist, biochemist, peace activist, author, and an educator, studied the theory of chemical bonding using the symmetries of orbitals. He received the Nobel Prize in Chemistry in the year 1954. Vladimir Fock, a Russian mathematical physicist who made seminal contributions to quantum mechanics and the general theory of relativity. The Hartree-Fock equation, improved by him in 1930, became a basic approximation method for calculations involving multi-electron atoms in quantum chemistry. In around 1935, he derived the spectrum of the H atom from the SO symmetry. In 1937, H. A. Young and E. Teller derived a connection between the symmetry of molecular configurations and the stability of degenerate molecular electron orbitals. In 1965, R. B. Woodward and R. Hoffman described how the conservation of orbital symmetry influences the course of molecular reactions, the Woodward-Hoffman rules. In 1984, D. Setchman found the first quasi-crystal in the laboratory with evidence of dodecahedral structure, one not expected to exist by conventional wisdom. And finally, in 1985, Curl, Crotto, Smalley, and co-workers produced the first observed C60 molecules.
Now, in this module, we have seen the symmetry products of symmetry operations. Rules and notations followed for performing symmetry operation has been explained. Effect of symmetry operation on general point groups in Cartesian coordinate system has been explained. Few examples of performing of symmetry operations have been discussed. In the end, some general points about relation between symmetry operation and symmetry elements have been explained. In example of trans-dichloroethylene, it has been shown that I and C2Z they commute with each other.